there be stuff from 8.1, 8.2, and 8.3 that we need for 8.4? Well, I tried to make sure when I went through the homework assignments that I took out any review problems that involved 8.1 to 8.3. And really, by going to 8.4, we're kind of doing the easiest stuff first, and it's what you're going to see on the MCAs and the ACTs. So we have to get that in before Tuesday, because that's when you're taking the ACTs already. So what we're going to do in 8.4 today, we're going to simplify rational expressions. That's our big objective here. Multiply and divide rational expressions. We're going to talk about multiplying today. We'll hold off on dividing for tomorrow's notes. So today we're simplifying and we're multiplying. Now, why is it easier to multiply and divide when you're talking about fractions than it is to add and subtract? Because if you want to add and subtract, you have to have a common denominator. So it takes extra steps to make that happen. We rewrite 1 as 1 over 1. Leave the little plus 1 over x alone for a second. And realize the least common denominator for 1 and x is x. Well, this one already has it, but this one doesn't. So I have to multiply the denominator by x to get a common denominator. But we all know that whatever you do to the bottom of a fraction, if you're going to keep it equivalent, you have to do the same thing to the top. So by multiplying by x over x, we really just multiplied by 1. We're going to make it look different, but it's going to have the exact same value. Now it would be x over x plus 1 over x. And now that we have a common denominator, we want to write our answer over that common denominator. So we look at the top and we see, well, it's just going to be x plus 1. Those aren't like terms. I can't do anything with that, so I have to leave it x plus 1. Now, here's what we don't do. At the end of this, we don't go, oh, wait, there's an x on the top and the bottom. I can cancel those. No, you can't do that. You can't cancel these x's. I've mentioned it 20 times in first and second semester already. Canceling is a form of division. To use division, you have to see pure multiplication. This has addition. We can't cancel that out. You need to see multiplication in order to cancel. And that's really what we're going to do today. We're going to be tearing things apart, making them look like multiplication to see if we can do some canceling, some simplifying. So, A, rational expression is the quotient of two polynomials. There come all the fancy words, right? Rational expression, the root word for rational is ratio. A ratio in math is a fraction. So we're going to talk about fractions. And quotient in math means division. That's what fractions represent. 3/4 is the same thing as 3 divided by 4 on a calculator. So quotient is division. Our essential understanding is it's easier to work with multiplication and division with fractions than it is to add and subtract. We can use much of what we already know about multiplying and dividing fractions and divide rational expressions. So it's not going to change what we know about 1/2 times 4. But it's going to look more complicated because we're going to have algebraic expressions in there. So rational expression is in simplest form when the numerator and denominator are polynomials that have no common divisors. You have canceled everything you can possibly cancel. You have it simplified. So to start with, we just need to see what does that look like, you know? So this one says these are already in simplest form. Smartboard's a little slow here. And I see x plus 1 over x minus 1. They wrote it kind of goofy. They've got a little comma here, but they're saying, here's 1. Yeah. I mean, I can't cancel that. One has addition and one has subtraction. They're not a perfect match. I can't do anything with that. But I look at x squared plus 3x plus 2, and I see there's an x plus 3 on the bottom, and I think, I wonder if I were to factor x squared plus 3x plus 2, then I'd have two sets of parentheses, and that's multiplication. Maybe I could cancel. So let's see. I need x times x to give me x squared, and then I need two numbers that multiply to 2 and add to 3. It's 2 and 1. Oh, that's why this one is in simplest form. Even though you can factor it, nothing's going to cancel out because there isn't a perfect match in the denominator. All right. Now, just so you know, this is not the answer we would leave if this were on a test, a quiz. We don't take quizzes in here, but if we did quizzes and tests, this is not what we would leave. This is, because this shows Cedarholm. I knew what I had to check for. I knew that I had to see if I could factor and then cancel. I can't, so I left it like that. That tells me you know exactly what you're doing. Now these, the first one says, oh come on, blue, turn on, there we go. X over x squared. Well, hopefully for everybody that's a duh moment. No, that's not simplified. You know, because we can cancel one of the x's out of the top and the bottom, and that would be 1 over x. Because exponents are really multiplication. X squared is x times x. Now the next one says 3 times the quantity x minus 3 over x minus 3. Cedarholm, there's subtraction in those two. We can't cancel them. But look at what we have outside that subtraction. We have parentheses showing multiplication. So we can cancel if we see a perfect match, and that's what this is right here. So this one would simplify to 3. Now that last one definitely has that look of, hey, I should probably be able to factor this and then see some things happen. So now we have to go back to all our rules of factoring, where we say, hey, is there a greatest common monomial factor I can take out of this? Neither one of them. There is not a number, a variable I could pull out of them. Hey, maybe they're special. Maybe these are one of those perfect square trinomial things. Nope. The last term has to be a perfect square for that to happen. So we just go to good old-fashioned factoring and say x times x is definitely going to get me my x squared. On the top, I need two numbers that multiply to -6 and add to -1. Help me out. What would those be? -3 and +2. On the bottom, we're going to need two numbers that multiply to -2 and add to 1. 2 and -1. Does everybody now see the multiplication? See how we have the parentheses, and parentheses show multiplication? So now if we have a perfect match, we can cancel, because canceling is division. And these two little buggers right here will be gone. Nothing else we can cancel, but those two will be gone. And it'll be x minus 3 over x minus 1. So we're talking about how do we know what's in simplest form. And it really goes to the, can we factor it or not? If we can factor it and see the multiplication, then yes, we can cancel using division. So to find those common divisors, we have to factor. And like it says, if possible, you know. Back when we were doing our factoring in first semester, every once in a while they'd throw one in the homework just to make sure we were checking for every possibility that said not factorable. But because this assignment is about factoring and canceling, you should expect that a lot of these are going to be factorable when you do them. Scared of this section so far? Okay, about 10 people are, no, it's not a big deal. Good, good. I know that lots of you are really good at factoring. I saw that in first semester. So a rational expression and any simplified form have to have the same domain in order to be equivalent. So we're not just going to do all this canceling. We're also going to let them know, hey, don't try and put this number in, because these are fractions. And if they're fractions, that means we might put a number in that would make the denominator 0. And that's the bad one because you can't divide by 0. So once we have those in factored form, we stop and take a look and say, well, I can't put a 1 in there because 1 minus 1 would be 0. So x can't be 1. And I also can't put a negative 2 in because negative 2 plus 2 would be 0. Now when I simplify it, the x plus 2's cancel out. So when somebody looks at this problem, hopefully if they know enough math, they'll say, oh, I can't use a 1. But without our little warning, they wouldn't know that you can't use negative 2 in this problem. So again, domain is our warning, our restrictions telling people don't try and use this number. Because when we were building this, we had to break it down a little bit. And what you can't see is that negative 2 can't go into this anymore. So in the example above, you have to exclude negative 2 from the domain because negative 2 was not in the domain of the original problem. What the author wanted when they wrote the problem, the author's intent. Note that this restriction is not evident if somebody just looks at your answer. They're not going to know that. They're going to think, what are they talking about? Don't use a negative 2. Negative 2 would work in there, but not in the original. So we have to be careful with those domains. All right, away we go. Simplifying a rational expression, what is x squared plus 7x plus 10 over x squared minus 3x minus 10 in simplest form, but also state any restrictions on the variable. Well, right now I can't give them the restrictions on it because I don't know what they are. I've got to factor this. So again, I start thinking, is there a greatest common monomial factor? Number or a variable I could pull out of the whole thing. And the answer is no. Maybe it's a perfect square trinomial. No, 10 and negative 10 are not perfect squares. So we are right back to good old-fashioned factoring, where we know x times x will give us x squared. And then we just have to do a little figuring. We need to figure out two numbers that multiply to 10 and add to 7. What are those? And for our denominator, we need two numbers that multiply to negative 10 and add to negative 3. What are those? Negative 5 and positive 2. But before we do our canceling, because I know we really want to do that, right now we have our best opportunity to talk about what numbers we have to keep out of here for the domain. So give me one number that's going to be bad down there. 5. 5 is out because 5 minus 5 would be 0. Give me another one. Negative 2. So those are the bad ones. So no matter what happens and what cancels as we move forward, we have to warn people, don't use these two. Those would be bad. So what did you see that cancels? Yep, now that we can see the multiplication with the parentheses, we can use canceling, which is division. And we know we can't cancel those x's. We can't try and cancel the 5 and the negative 5. We can't do that because that's not pure multiplication anymore. This is addition and subtraction. There it is. Alrighty. A looks different. Well, we're not talking about quadratics here, so we're not going to really factor these. This is a lot like what we did when we were doing the MCA review. Do you remember it? But before we get started with the canceling, we need to warn people, don't try and put this in for x and y. What would be a bad number for x? Yeah, because then you'd have a 0 in the denominator, so x can't be 0. What would be a bad number for y? 0, because you have a 0 in the denominator. So we start there, and then we think, all right, let's cancel. whatever we can. I'm going to rewrite it though so that in the notes people can see what the original problem was. Alrighty, so we've got 24 and 6. 6 goes into both of those. It'll go into 24 4 times, and it'll go into 6 once. But I noticed the negative, and I'm kind of worried I'm going to forget that it's down there. So it doesn't matter if it's in the bottom or on the top. I think I'm going to move it up here to the top so I don't forget it. So it can go either way, and usually mathematicians put it on the top. We just do, so it gets everybody's attention right away. How many x's could you take out of the top and the bottom? They both have, you're looking for the smallest that we see there, and they both have 2. So we'll take x squared out of the top and the bottom, and that'll leave us with an x to the first on the top. How many y's would we want to take? 2. Yep, we've got a y squared here. That'll become a 1, and that'll leave us a y in the denominator. Again, just be organized, and then you can keep track of everything. So on the top, we now have a negative 4 and an x times 1, which is negative 4x. On the bottom, what's the only thing I have? Just y. But again, we covered the domain restrictions right away, so they'll know. Hey, in fact, if they looked at this, they'd think we were pretty silly putting that x not equal to 0 up there. But if they look back, they'll realize, oh, there was an x in the denominator when they started. That's why you can't use that. Alrighty. Is B the same type of problem as A? No, got to do some factoring, right? Because we see our quadratics up there, our x squareds. Let's see. No greatest common monomial factors. Negative 8 and positive 6 are not perfect squares. We're doing a lot of good old-fashioned factoring today. So please give me the 2 numbers that are going to make our numerator work up there. Plus 4 and negative 2. And the 2 numbers that will make our denominator work. Negative 2 and negative 3. Before you cancel, remember, we did this so we could see the domain. So what numbers are out for x? 2 and 3. And we can cancel what? X minus 2's are gone. Anything else we can cancel? X plus 4 over x minus 3? Done. And we definitely told them about the domain, so it's good. So right now all we're doing is simplifying, because this is one fraction and we're trying to see what can be broken down. Alrighty. C looks different. So I go through my list. First thing to always check with factoring is, can I factor out a greatest common monomial factor? Oh, this time we can. Look at the numerator. What could come out of both of those terms? Well, let's take it out of there. I think I'm supposed to know how to factor that bottom one. I think that's a special pattern. Anybody remember the name of that pattern? Difference of 2 squares. They're perfect squares. So I have to think, how did we get it so there wasn't a middle term again? Oh, one was a plus and one was a minus. That way outside times outside and inside times inside canceled out. Stop right now and do the domain. I'll put it down here. What numbers are out? 3 and negative 3. So maybe we'll just write this one, x not equal to plus or minus 3. I'll take care of it. You can write them separately too. It doesn't make any difference. Well, I can't cancel anything. My parentheses aren't exactly the same. But hopefully you notice this. Do you see how this is backwards of this one? So I think for a second. I think we know what we could do that would change those signs around. Anybody remember what you can factor out of something to change the signs? A -1. So we'll make this a -4, and that's going to reverse that -x plus 3 and make it positive x minus 3. Now that doesn't change our domain, because all of that work was in the numerator. But now we can cancel. Now we can simplify it. We can take those x minus 3's out of there. And now it's done. So to reverse the signs, all we do is factor out a -1. That's it. So this was simplifying, and they had to see a lot of different things here. You know, we had a greatest common monomial factor, good old-fashioned factoring. We did some basic canceling, and we did looking at the difference of two squares patterns. So there's a lot of patterns that we know from factoring that we can use. Now, how does this change if it says, we'll take two of these now and multiply them together? We still have to factor absolutely everything. The good news is we might have more opportunities to cancel, because you can cancel any perfect match in the numerators with any perfect match in the denominators when you multiply. It doesn't matter which fraction it's over or under. Anything in the top can be canceled with anything in the bottom that's a perfect match. So this says, what is the product of x squared plus x minus 6 over x minus 5 times x squared minus 25 over x squared plus 4x plus 3 in simplest form? And of course, state any restrictions on the variable, so the domain. All right, x squared plus x minus 6. There's no greatest common monomial factor. -6 is definitely not a perfect square, anything. So that would seem to be a good old-fashioned factoring problem there. What two numbers should we use? 3 and -2. X minus 5, isn't that already in factored form? So really, if it bugs you, you might want to put it in parentheses. Sometimes that helps students visualize, hey, that is a perfect match somewhere else. Now, we're supposed to take that times, x squared minus 25. I think that's a special one. That kind of looks like the one we did on the last page, which was x squared minus 9. So how does that factor? You're writing like crazy. You're already doing this one. How did you factor x squared minus 25? Right. Denominator, we look at it, not a perfect square trinomial. It's just good old-fashioned factoring. And like I said, I already know you were doing this one. What numbers did you use for that one? 3 and 1. Now, I know it's hard not to start canceling right away, but we have to stop right now and talk about the domain. We have to. We've got 3 different factors down here. So, for the first fraction, what number's out? 5. It's out. For the second one, what 2 numbers are out? -3 and -1. Now we cancel. And like I said, the benefit of this being multiplication is any perfect match on the top of either one of these fractions that matches any perfect match on the bottom there, we can cancel out. So it doesn't matter that x minus 5 is under the red fraction and then it's on the top of the black one. That makes no difference, because when you multiply fractions, you do top times top and bottom times bottom. So it would be canceled out anyway. Anything else anybody saw and canceled away? What else? Is that everything? No more perfect matches left, right? So then you just collect it up. Top times top bottom times bottom. Always gives you a chance to double check. Hey, did I miss a factor that's a perfect match here? Or maybe there's one you could turn around backwards. Nope, that's done. So we do the domain as soon as we see what all those factors are for the denominator, and then we simplify by canceling. All right, let's look at this one. We've got 2x minus 8. What do you notice about that one? Yeah, greatest common monomial factor. Hey, x squared minus 16, that looks familiar. How does that factor? Yep, difference of two squares. And we're multiplying again. X squared plus 5x plus 4. Hey, this gives me a chance to remind everybody about perfect square trinomials. If this is a perfect square trinomial, the first term and the last term are perfect squares, which they are. But we also have to check the middle term. So you think, well, what did I square to get x squared? I squared x. What did I square to get 4? 2. And here's how you check the middle term. If you multiply 2 times x and then double it, it has to equal the middle term. Then it's a perfect square trinomial. This one doesn't, but I wanted you to see that because you're probably going to have a perfect square trinomial in the work that you do, the homework today. So it means good old-fashioned factoring again, which some of you have already done. I can see that. What numbers did you use? 4 and 1. Now on the bottom, x squared plus 8x plus 16. That might be another perfect square trinomial to check out. This is x squared. This is 4 squared. If you take x times 4 and double it, what do you get? This is a perfect square trinomial. Now that means we could write it as x plus 4, the quantity squared. But I will tell you, most Algebra 2 students don't like to write it that way. Can you see why they would want to write them out separately? What's the advantage? Easier to cancel it, right? So, if we were just factoring and testing you on factoring, you would have to write it this way. That's not what this problem is about. This problem is about all that wonderful canceling you're going to do. So with this one, you probably want to write it out twice. Now, that wouldn't be good for an answer, but we're not at the point yet where we write the answer, because we want that in simplest form if we're going to do answers. We're at the point where we can talk about domain. That's where we are. We have everything factored. All right, what numbers are out thanks to this first denominator? Yep. Can we add to that list? Didn't give us anything new, did it? And now we can cancel, hopefully lots of things. What did you see? Yep. So we take 1 for 1. You have to match one perfect set with another perfect set. And then the x plus 4s. Now notice I took 1 from the first fraction and 1 from the second. If you're like, but Cedarholm, I did these two right here. Big deal. Doesn't matter. You're going to have the same amount in the end. Anything else? So on the top, we still have a 2 and the quantity x plus 1. And this was what I was talking about a minute ago. I don't want to write it as x plus 4 times x plus 4 for my answer, because that's not really simplest form. Simplest form is to know that that means x plus 4 squared. Now, I'm not going to take off on the test if you write it as x plus 4 times x plus 4. And like I said, most Algebra 2 students would just rather leave it that way anyway, so that they don't, miss it when they're going through. But that's how we do our multiplication. So, want me to make up another one of anything, or are you feeling pretty good? We got it? Okay. Well, I know you'll be disappointed to hear that I actually forgot to take off a couple of problems off of this one that were from 8.1 to 8.3, so you can't do these. I'll make it up to you another day. 8 through 19, 50, and 52 are what we're working on today. And since some of you are super fast at this, you might finish this before you go. But don't forget the domain part. You know, I know we get so fast and carried away at all the wonderful canceling we can do. Sometimes we forget about those domain restrictions.